Hello, my name is Aubrey Goff. This is my Physics 1 lab on constant velocity. So to start off, we're going to start by looking at a computational model for constant velocity. And this program was given to us by our instructors and edited just a little bit to kind of show what exactly we should expect from constant velocity from a computational model specifically. So this here you can see is going to be our starting point at this little yellow ball, and our final position is going to be this blue ball, our object in question. So when we move down and look at our position versus time graph, what we're seeing is an increase in our x position specifically that you can see here in this image because there's no change in our y velocity whatsoever. This constant velocity is only in the x direction. And we would expect to see a linear relationship between position over time because it is a constant increase in our position with respect to time. And when we take the velocity of that actual motion, which in this case is going to be 1 in the x direction, that stays constant throughout the entire movement of the object. And this is because, as I mentioned earlier, this is a constant velocity in the same direction. So we would expect to see a flat line in our velocity with respect to time graph, which actually this is a derivative of our position versus time graph. And this can be seen in our results here. This is giving us our time on the left, and on the right is our velocity. And as you see, that's constant throughout the entire movement of our object. Now, when we're looking at motion in real life and in a real scenario, this is going to be more of what we're seeing. And as you can see here, this is an expo marker that's been rolled across the table. So starting from here, this first of all is just our calibration stick. It's just going to give us a measurement of space. So as we watch this expo marker roll across this table, we can see there's not a real change in our y direction, which is to be expected. It does look a little bit funny over here, but that's just more due to human error because I was the one detailing where exactly this expo marker is in relation to our coordinate plane. But as we can see in this top right graph here, this is our position with respect to time graph in the x direction. And that is showing us that there is a linear relationship here, which we would expect to see from an object with a constant velocity. So this means that our computational model is a good representation of actual motion. Now, the discrepancies that we see here are probably due to friction here on the table, air resistance, as well as human error, as I mentioned previously. But these all still fit within the computational model, which means that it's a good representation of real motion. Now, this is also indicative that there's no F net because there's no acceleration, which means that, again, our velocity is constant. So our key assumptions here when we're making this computational model is that we're negating air resistance, friction, we're assuming a constant velocity, and we're also assuming accurate initial conditions, which should fit here. Now, if we were to change the movement of this marker, say from the positive x direction, which is what we're seeing here, to the negative x direction, we would see the exact same motion, just in reverse. We would see this marker moving to the left instead of the right. And the magnitude of our velocity, our actual velocity itself, would not change, but the direction would change. Speed is not changing, velocity is changing direction. Really no movement in the y direction. It seems that there is just here, but these numbers are so small it kind of, for our purposes, negates the movement in the y direction. So this means that our computational model that we saw earlier is representative of real motion, and it is indicative of constant velocity.